National Electrical Code (NEC) does not specify a maximum distance for a grounding wire to run from the main breaker panel. However, general recommendations suggest keeping the grounding wire as short as possible. This minimizes resistance and ensures a proper ground connection. When a water main is located on the opposite side of a building from the main breaker panel, the grounding wire can be run through the building. It should be installed within a conduit or another NEC-approved method. Despite the routing, always strive to keep the length of the grounding wire to a minimum. Securely connect the grounding wire to both the water main and the main breaker panel. It is important to understand that the NEC does not mandate a grounding wire connection to the water main if other grounding electrodes are available. Acceptable alternatives include a metal underground water pipe system if it meets specific requirements, or a grounding rod. Connecting to the water main is often favored. This preference arises from its ability to provide a low resistance path to ground. It is generally less prone to damage compared to other grounding electrodes like ground rods, which can corrode or be affected by soil conditions. When determining the appropriate size of the grounding electrode conductor, refer to NEC Table 250.66. This table correlates the size of the ungrounded service conductors or equivalent area for parallel conductors with the required size of the grounding electrode conductor. The grounding electrode conductor connects the service equipment to the grounding electrode. If using a ground rod or ground plate electrode, the grounding electrode conductor never needs to be larger than 6 American wire gauge copper wire or 4 American wire gauge aluminum wire, as specified in NEC Section 250.66 and 250.66b. For a concrete encased electrode, often called a U for ground, the minimum size is 4 American wire gauge copper wire. Remember to always consult the latest edition of the NEC and local amendments for the most accurate and up-to-date requirements. Local jurisdictions may have more stringent rules than the NEC. The goal of grounding is to provide a low impedance path for fault current to return to the source. A longer grounding wire increases impedance, which can impede the clearing of a fault. Impedance consists of resistance and reactance. Resistance is the opposition to current flow in a direct current or alternating current circuit. Reactance is the opposition to current flow specifically in an alternating current circuit caused by inductance or capacitance. Inductance is the property of a circuit to oppose changes in current flow, while capacitance is the property of a circuit to oppose changes in voltage. A longer grounding wire can increase both resistance and inductive reactance. When installing a grounding wire, avoid sharp bends. Sharp bends increase impedance due to the skin effect, where alternating current tends to flow more on the surface of the conductor. Use smooth sweeping bends to minimize this effect. Ensure all connections are clean and tight. Corrosion can increase resistance at connection points. Use appropriate connectors listed for the purpose and follow the manufacturer's instructions for proper installation. Regularly inspect grounding connections for signs of corrosion or damage. Replace any damaged or corroded components immediately to maintain the integrity of the grounding system. Consider using exothermic welding for grounding connections, especially in corrosive environments. Exothermic welding creates a permanent low-resistance connection that is highly resistant to corrosion. When running a grounding wire through a conduit, use a metallic conduit for added protection. The metallic conduit itself can contribute to the grounding path, providing an additional layer of safety. Make sure the conduit is properly bonded to the grounding system at both ends. This ensures electrical continuity and minimizes impedance. In some cases, it may be necessary to use a ground fault circuit interrupter (GFCI) to protect circuits. GFCIs detect small imbalances in current flow and quickly interrupt the circuit, preventing electrical shock. GFCIs are particularly important in wet or damp locations such as bathrooms, kitchens, and outdoor areas. When selecting a grounding electrode, consider soil conditions. Soil resistivity can significantly affect the performance of a grounding electrode. Conduct soil resistivity tests to determine the most effective type and placement of grounding electrodes. Low soil resistivity is desirable for effective grounding. If soil resistivity is high, consider using multiple ground rods connected in parallel to reduce overall resistance. Space the ground rods at least the length of the rod apart to avoid overlapping spheres of influence. Adding ground-enhancing compounds can lower soil resistivity. These compounds are typically made of bentonite clay or other materials that improve the conductivity of the soil. Consult with a qualified electrical engineer or electrician to design and install a grounding system that meets the specific needs of the application. Grounding requirements can vary depending on the type of building, the electrical system, and local regulations. Always prioritize safety when working with electrical systems. To energize circuits before working on them and use appropriate personal protective equipment (PPE), such as gloves and safety glasses. Proper grounding is essential for electrical safety. It protects people from electric shock and prevents damage to equipment caused by ground faults. A properly installed and maintained grounding system provides a safe and reliable electrical system.